Hey everyone, we're here to talk about derivatives today, and specifically derivatives applied to vector functions. This is a thing I wrote in Desmos just to take a look at vector function and how the derivative can be visualized in a couple of different ways. So right now, you'll see I have my v of t defined as 0.5 sine t, cosine t, 0.2 t. So this is sort of an elliptic spiral. If you look top down, you'll see kind of in this y direction, I'm going 1. So that's this cosine that's right here, taking me 1. In the x direction, I have this 0.5 sine t, so I'm only moving 0.5. And we're just tracing out this ellipse through that whole thing. And then the z is this 0.2t, so that's increasing the height of the function in the z direction as t gets bigger and bigger. So normally I might view it this way, the x on the left, y over here. It's kind of hard to see the vectors that are drawn there, so I'm going to rotate that around so we can get a better view. So right now the green, this is my v of a. So this is kind of my initial point, right? V of a. We got a vector pointing from 0, 0, 0, the origin, to that v of a. So that's this green vector right here, just pointing there. So this is what I'm thinking of as my point I'm interested in, my initial point. Now, the derivative, you may remember from Calc 1, is the a limit of the difference quotient. So the difference quotient in this case would be if we take a little further distance down our variable t, so like t plus h, and we just take the v of that t plus h minus the v of a, and then divide by h. That's going to be our difference quotient. And then we'll take a limit as that h gets smaller and smaller and smaller, meaning this blue point will get closer and closer and closer to this green point. So I have that kind of listed here, a v2. So that's vector with tail at the origin, pointing at v of a plus h. And we'll take this difference quotient right here. This is my v3, which is the purple vector right here, pointing from that v of a. So I'm starting at v of a, going to this v of a plus h. That distance and then divide by h gives me the length of that vector right there. And then the v of a that you'll see here, that just means I'm putting my tail at that point, v of a, at that green point. So I'm going to go ahead and animate this h. Right now it's at 0.5. I'm going to take that closer and closer to 0. And we can see that purple vector kind of changing as I do that. So that it's more like what you can think of as a tangent line, right? So, but this time we could call that maybe more of a tangent vector to that curve at that point. So again, just taking that difference quotient and then the limit as that point gets closer and closer to my original point is going to end up just with that tangency that I'm used to from Calc 1. Now, a couple things that you might want to consider are vectors don't always have to be placed in a certain position. So in fact, if I go ahead and put in a couple things right here, so this is going to be the same vector, but with my tail at the origin. So instead of tail at that point VA, I just have my tail at the origin. And if I go ahead and trace this around, so I'm going to kind of move my A around. So depending on what A I start with, right, will give me a different vector. If I just trace out the head of this vector when the tail's at the origin, this is my vector function. So this is my derivative function of that v of t that I started with. So we call that v prime of t. That's the usual notation. And it's just this one, right, closed curve, because the derivative of this, z component is going to be a constant. So really I'm at that constant height of 0.2. You can kind of see that if I change the orientation here. And then it's just going to trace out that ellipse over and over and over again, because we'll get just another cosine t and sine t in there So it's just going to trace out that ellipse at that constant height of 0.2. So that is my derivative function there as it traces out with that derivative vector kind of pointing from the tail to the end of that path, depending on what value of a that I'm plugging into the function. You can also visualize it as over here, right, on the actual original curve as a vector that is tangent to that original curve. So if I zoom in far enough, right, this would look like a line and it would match that vector that's right there. Now, a lot of times what you'll see is if we normalize that vector, so thinking of this as sort of my tangent vector, if we normalize it, then this would be a vector of length 1, and depending on where I'm at, those lengths may not always match, right? So this is kind of a shorter vector, but this red vector is still length 1 right there. So normalizing that to a length of 1, this is normally what you would call big T of t. So that would be our defined sort of tangent vector function, big T of t. And it's basically just the derivative, but normalized to be length 1. So just a couple visuals so you can see kind of what we're talking about when we look at vector functions and tangent vectors to a curve. I'll go ahead and change tabs real quick and talk about integral functions. So in this one, again, we're just trying to get a visual of what's going on. So I've changed my function just a little bit. So now it's sine t, cosine t, 0.2t again, but I don't have the 0.5. So this is more, if I look head down, more of a circular pattern that I'm tracing around, but the t is increasing as I go. And so the derivative, just like last time, would be a circle at this height of 0.2, as I go around. If I just keep my tail at the origin. This time, though, we're going to want to integrate and see what happens if I integrate from a to b. So right now what you can see is I've sort of chopped up, right? What do you do when you do an integral? You chop up something into a bunch of pieces and you add up those pieces. So I've chopped up this curve into a few different pieces. So right now we have it at 10. If I want to take this down to like 6, I'm going from a is 0 to b is 6. So this would be thinking like this definite integral from 0 to 6. We're going to kind of estimate right now with the Riemann sum, and then we'll take a limit in a minute. So this Riemann sum, if my b minus a is 6, my n is 6, right? The delta x is that b minus a over n, so that's just going to be 1 unit of time. So these intervals right here are what's covered with 1 unit of time. So I'm going this teal, and then this blue, then this little bit darker blue, purple. So these are kind of 1 unit of time being traced around that function. And the vectors that are pointing to the beginnings of those intervals are just the vectors that I'm going to try to add up, right? So Riemann sums are going to add things up. So we're going to pick a vector in each of those intervals, and we're just going to add them up. I can go ahead and kind of view that here. Now, how do you add vectors, right? You usually place them tail to head, tail to head, tail to head, all the way across. So if I just put these vectors in a different spot, right? So that I'm starting here, and then I'm using this vector as my first one, this vector is my second one, so I'm sort of using this would be a right-hand sum because I'm using the right point or the last point in that interval each time. I would get something like this. I can change that if I want, right? So if I wanted to use, say, the first vector or something like that, I could do that, but this is what I get right now. So this is what we're tracing out through this thing. Now what I can do is take a limit, right? So this is my Riemann sum. This is where I would end up. And if I want to draw in that vector, this orange one from the tail to this head, that would be my final vector that would come out of my Riemann sum. So this will be the result. So our result is going to be just this vector that goes from here to here. Now what we'll go and try is taking a limit. So I'm going to come back up here, increase my n. So these intervals are going to get shorter and shorter, and these vectors will get smaller and smaller. So as I decrease my n, right, these vectors are going to get shorter and shorter because they're being scaled by that delta x. And I get more and more pieces, but smaller and smaller pieces, right? So you can see these vectors really shrinking as they go down toward the origin. So if you zoom in, it's just a really short vector from the origin to not very far along that ray that goes to these interval points that are still around the curve. But then I'm just going to start them here and add them up as I go around. And so again, we're just placing all these really tiny short vectors, tail to head, and adding them up. And I end up with some vector that takes me from the origin all the way to up here. The final vector, this v of b minus v of a, if I actually took an integral, so this big V is defined as sort of my antiderivative here, right? That would be this blue vector, and this V of t, big V of t, right? This is my antiderivative, which I can think of as my integral function. And you'll notice that this just kind of traces that path, maybe not exactly with these, this is an approximation with the vectors, but as that limit gets better and better, it's going to get a better and better approximation of that final vector function that's right there, which would be my antiderivative or integral function. And so if you want to keep going, right, with these, you can just see that orange that used to be like, way over here. Not a very good approximation with only n is 6. But as that n gets bigger and bigger, I get a better and better approximation to that actual final, limiting value, which is the integral function, which is this green curve, or the definite integral, v of b minus v of a. I'm thinking a big V is that antiderivative. So kind of fundamental theorem of calculus part 2. At least most books call it part 2. So that big V of b minus big V of a, that would be this vector, that blue vector that goes from there to there. So that's kind of what's going on behind the scenes when you're taking integrals. Luckily, the computations aren't too hard. With vectors, derivatives, you just go piece by piece. IJK components. Integrals, same thing. You just integrate IJK components. But this is kind of what's going on behind the scenes. Why that all works is just how sums work with vectors, and back with the derivatives, how that difference quotient limits out to the tangent. So hope that was helpful, and I'll see you on the next one.